Hello, my name is Kaleb and Naveed, and I will be presenting my work from the Robotics Institute Summer Scholars Program. My mentors are Ms. Deakin and Dr. John Dolan. My project was trajectory planning for autonomous vehicles using hierarchical reinforcement learning under noisy observations. Our main work was to make the reinforcement learning framework for trajectory planning more robust. So for that, we divided our problem into two parts. The first one was to plan safe trajectories. And for that, we used hierarchical reinforcement learning and the PID controller. The second one was to handle incomplete observations from the noisy perception system of the car. For that, we used recurrent neural networks, and in particular, the long short-term memory there. The previous work on trajectory planning includes both rule-based methods and machine learning methods. One of the rule-based methods, rapidly exploring random trees, generate trajectories by building a tree-like structure through space. RRTs are computationally costly and do not guarantee optimal solutions. Another approach is imitation learning. This method is not considered safe and stable as it directly relies on human driving patterns, which can be highly unpredictable, and thus this method cannot be generalized to complex conditions. Another learning method is reinforcement learning. The traditional RL framework requires higher training time and has low safety guarantees because of the direct use of low-level actions, which include throttle, steer, and brake. We use the hierarchical reinforcement learning framework in order to plan trajectories, and the scenario we used was a lane change scenario in which the ego car has to do a lane change, but it also has to consider traffic in the target lane. For our hierarchical structure, we use two meta goal options, which include a lane follow / wait option, and the other one is lane change. For each high-level option, we give car 3 low-level action options, and once car selects the low-level action, then the PID controller is used to drive the car. Let's suppose that our car selected the lane follow / wait meta goal option. Then the black line shows that the car can follow lane for a greater distance as it does not see any obstacle in front of it. The red line shows that the distance between the ego car and the obstacle is decreasing so that the car can follow lane for a shorter distance. The yellow line shows that the car has to wait because the distance between ego car and obstacle is less than the safety threshold. On the other hand, if the lane change meta goal was chosen, under this meta goal, car is also given 3 low-level actions, and ego car selects action based on its previous velocity profile. Once the point is selected, then there is a point that is given to the car which is called safety follow point, which makes sure that car can reorient itself before the charge is given to the lane follow / wait option. For the state space, we use ego car velocity, obstacle car velocity, ego car distance to obstacle car, target A car, target B car, and to the goal position. For our reward structure, we use a hybrid reward structure proposed by ZQN and al. So there is a separate goal reward for the goal, for action, and then the task reward is the summation of goal and action reward. We give car collision penalty and lane invasion penalty, and we also give car safety reward. In order to deal with noisy observations, we use LSTM layer. This figure shows the details of our network which we use, which was dueling double DRQN. We use a separate network for option and action. For LSTM layer, we use 3 time steps and the bootstrap random updates. We ran experiments on the Carla simulator with 10 frame rate per second, and we randomly changed the velocities of target car for uncertainty during experiments, and we also added noise to the state space. This is some of our preliminary results. In this, the front green car has higher velocity, and the ego car can be seen doing lane change. The red line shows that the ego car is following the lane following option, and the yellow line shows that the car followed the lane change option. This slide shows a scenario when both target cars are moving with the same speed, and the ego car is waiting and then doing a lane change maneuver. This slide shows that when only one of the target cars is moving. For future work, we want to compare our technique with other techniques, for example, slot-based methods, and we also want to experiment with adding more noise to the data, to the state space. And we also want to test our structure on other scenarios, for example, traversing intersections or lane merging. At the end, I want to thank RISC sponsors, RISC coordinators, and my mentors for their continued support throughout the summer. Thanks for listening.